All right, so I had actually just recorded a whole video, and of course what ended up happening is I didn't realize that the video quality was going to be really poor. Basically, let's say, 1 or maybe somewhere between 5 and 10 seconds per frame. So basically, what should have been a nice video showing you a bunch of great things became a slideshow. If you saw that video, my apologies. I've unlisted it, and I'm gonna link it to this video so that hopefully people get a chance to see the things that I was trying to talk about. So this is take two. Hey guys, so it has been a while. I had a new job that started a little while ago, and that's definitely been taking up a lot of my time. But even with that being the case, I do have some things to share. There's some progress that's been made, and I'm really happy with some of the things that I've managed to do. So let me get right into it. To start, I'm going to give you just a little demo of what I'm talking about. So it says it in the video title, but let me pull up the video capture here. So you'll see here that we are still using the same 16-bit background layers, but there's something new. So there is now a date time timestamp in here, and that timestamp is being added into the display on the FPGA from a program that I wrote that's running on the ESP32 chip that's on the Spartan accelerator board. That program is blasting data over to the FPGA using the QSPI bus, that's the quad SPI serial bus, from the ESP32 to some custom designed hardware within the FPGA that's able to receive that information and then write that data to the block RAM, which then becomes the data that the graphic system on the FPGA will use to go ahead and pick what information to render for each of the background layers. So that means for the first time, we now have a meaningful transfer of data from an application on the ESP32 to the FPGA to the FPGA block RAM, so that we can start to manipulate the graphics that are being displayed with this design. So I'm really thrilled about this. It took much longer than it should have, and I'll walk you all through the things that I've tried, how the solution works now, and the things about the solution that still don't work right. So with all that said, let's just go right over to Vivado. I'll shrink this back here a little bit. All right, so if we come into Vivado, most of the code, most of the design for the graphic side of things is unchanged. There's really hardly any differences. You can check the commit logs to see if there's anything interesting, but I don't believe so. So most of the hierarchy of the display is unchanged. The graphics compositor is where we start to see some changes. So like I said, the drawing side of this is really hardly different, but what has changed is if we follow this hierarchy down, you'll see the graphics compositor now has a RAM, its RAM component. The IP for that is changed a little bit. And then there's another component here, a SPI RAM controller and a SPI receiver. These are both components that I designed myself, and the simple RAM is still the standard Xilinx IP for block RAM. So I'll just open this up, because the one thing that changed here that I want to point out is in previous versions there was just one port on this RAM, and it is now a dual port RAM. And the idea here is this way the ESP32, when it writes data, it uses its separate port, port B, which is a writing port, and the graphic system uses port A to read data when it needs to. I still don't want them to happen at the same time, but when I tried to implement this by having a single port and moderating or like mediating the requests to read data and the request to write data from different sources, I was running into too many timing issues that were resulting in glitchy display, no display, and just too many problems. It simply wasn't worth it for this project to try and have this all happen in a single port. Anyway, the way that the block RAM works, I think this uses hardly any more of the FPGA resources, so it just makes sense in this case when we have, separate reading and separate writing systems to separate them entirely. So I set this up as 2 ports now. The other small change that I made is I added a new coefficients file that is the RAM data as same as before, except I actually added a section that has alphanumeric font at the start of the file. So the tile map definition starting at address 0 covers the letters of the alphabet, a few common symbols, and numerals 0 through 9. That way I can reliably address those tiles and put them into my tile map from my background layers, so that I can do things like have the numbers and text letters as you can see them now working. So diving in a little deeper now, the SPI-RAM controller, I won't belabor this because I think some things may need to change, but basically the design here is that there's a SPI receiver, which is what actually is getting the signals from the ESP32 and interpreting those SPI signals into data. The SPI-RAM controller then receives each of those blocks of data in the form of 16-bit words and knows which RAM address each of those words should be shared with, and then this SPI-RAM controller then is what is connected in to our RAM. So if we look, for example, here at the graphics compositor, we'll see our RAM is right here, and so we have a set of writing address and data A, right, which is the port that's being used by the SPI-RAM controller, and then we have clock B, address B, and data out B, which is what is being used by the graphics system to read the data from the RAM. So these are what is hooked up into our SPI-RAM controller. Basically, it kind of works similar to DMA in that there's no processor that's writing this data, so it's dedicated hardware. So I went ahead and called it DMA style writing. So there's a write enable address and data, and each of those comes from our SPI-RAM controller down here. So in the SPI-RAM controller, we get to have some fun. We read the data coming in from quad SPI, which, if you're not familiar, is basically similar to the standard SPI bus communication, but it uses four IOs for the data. So it can send 4 bits per clock cycle, where a standard SPI is going to be sending 1 bit per clock cycle. So it allows us to send a tremendous amount of additional data. So the way the SPI controller here is implemented, what I did was I created a state machine. It's been a long time since I made one of these, actually. So there's been a lot of fumbling with this. Honestly, I ran into many issues along the way, and I will tell you about some of the issues I still have as well. That I need to solve. But basically, the idea is anytime a new transaction begins, we then will first receive the address that the memory write should begin at, and then with every additional word, 16-bit word that we receive, we will then write data to that address. And once we've written data to that address, we will then increment the address so that the next word that we receive of data writes to the following address in memory. So this is our state logic, and then our output logic over here takes care of things like actually incrementing the address, keeping track of the data that's coming in, sending out this pulse message, which actually is the pulse which tells the RAM to write the data that it has on its data in line. and so on. So relatively simple design. It took a lot of time to get here, but anyway, that's what it does. So the SPI receiver is actually the piece that receives data directly from the ESP32 itself. The SPI receiver has no concept of addresses or anything. All it really does is it pulses every time it receives 16 bits of data, and we let our controller figure out where that data should go, what the meaning of that data is. So this is pretty simple. It's driven by the clock of the SPI bus itself, and just keeps shifting in 4 bits at a time. And once it's reached 16 bits for a word, then it's going to write out that data, and it's going to pulse. Here it is. It's going to pulse every time it then gets those 16 bits. So that's really all that's happening on the FPGA side. There isn't actually a lot going on here. One thing I wanted to point out was to look at the schematic for a second. So if we open the constraints file, you will see that I had to add the QSPI lines from the ESP chip here, and I picked up the pin mapping for each of them. So this came from the schematic for the Spartan Edge accelerator, and I hope, if you've been following the kinds of things happening with this channel, with this device, that you've already downloaded a copy of these schematics yourself. But short version of it, just to show you. So this is all of the pins that are on the Xilinx XC7S15 on the board. And if we come in here, it honestly it's basically impossible to try to figure out what's going on. So instead, the right way to approach this, what I did was I looked at the ESP32 chip instead. And over here, you'll see ESP QSPI D, ESP QSPI CLK, CS, and a few other pins that are marked as being for the QSPI on this chip, QSPI Q up here, right? So all of these. So basically from here, you can get the name of the pin, and you can, we'll need this for later, GPIO 2219, etc., from the ESP32. But from here, if we go ahead, we can actually, hopefully, sometimes this search is a little buggy, but basically now that we know the name of the pin, it's really just a matter of finding it on the page for the FPGA, and then from there we can get the pin that's required, and we can update our constraints file to include that information here. Fortunately, right, all these connections are 3.3 volts, so any kind of communication like this is actually pretty easy to set up once you take a look and study the schematic. So let's talk about the other side of this, which is the ESP32 side, the software side. We've been talking about the hardware side for a little while now. The software side, I gotta say, I'm not thrilled with the software side of this. I ended up implementing a project using the ESP IDF. I really want it to be in the Arduino library. I think Arduino is much more approachable for a newcomer. It's even just a lot easier to set up. This was set up in Eclipse, and honestly, it was pretty messy. And I think that if I take some time later, I can port some of the required functions, or make some of these required functions available within the Arduino environment. But basically, the reason why I was doing this with the ESP IDF is because it's not easy to use this QSPI peripheral. Honestly, even the documentation about QSPI for the ESP32 is not great. It's mostly focused on using the protocol to read and write data to flash memory, and connecting to specific brands of flash chips and things like that. And that's not what we're doing here. And fortunately, I, after a lot of searching and scraping of GitHub and forums and whatever documentation I could get my hands on, I did find instructions on how to set up the QSPI using the ESP IDF for kind of arbitrary transactions. So I get to have a lot of control over what data sent and when. So the short version of how we do this, so we send QSPI transactions, right? So we send 4 bits per clock cycle using dedicated hardware in the ESP32. The version that's in here right now is set up to send data at 10 megahertz, right here. It is capable of going at up to 80, and I'm still debugging a few other things. I didn't want to add the complication. I have found that it runs successfully at 80 megahertz, which is a lot of bandwidth. Basically, if you do the math, during the blanking period of the video being displayed, we can send about 23 or I think 26 kilobytes of data from the ESP32 over to the FPGA. So we can do that 60 times a second, and that means within 2 frames of video we can replace all of the data that's in our video memory, which is quite good, and I think will allow for a lot of interesting graphical capabilities for enterprising people. So most of what you see here is just a tremendous amount of code to set up the transaction itself. The way we start it is we set up an address. The first thing that we send over in our transaction is a 16-bit address of where we want to write within our video memory. After that, we fill the rest of the transaction with ASCII time. So we initialize our time up here, and because right now the system isn't connected to the internet, so it just relies on its timekeeping. Basically, when the program is run, it gets a default start time, and it just keeps ticking the time after that. But anyway, so as time keeps passing, we keep calling ASCII time, and then I wrote a little function which takes each of the ASCII values of each of the letters and numerals and translates it to the correct memory address for the FPGA to be able to register. So the first byte, so we have to send 16-bit words for each tile, and basically, if you might remember, right, we kind of copied the format of the SNES tile map, and so the last 9 bits, so the second byte and the last bit of the first byte are used to denote which tile should be used, and then the first 7 bits up here up front are for the vertical or horizontal flipping. It's for the priority, and it's for selecting a palette. So I specifically designed this to be easy for me to use for this kind of demo. So all of my letters and numbers are right at the beginning, so they all have values of 255 or less for their address. So we don't have to use the highest order bit within our first byte. And so up here we're just selecting 0x10, which is going to give us a good, nice black and white palette, as you can see, for our time that gets printed on the screen. And for each of the letters, we just do a little mapping based on a little bit of math to get to the correct letter or number based on a little bit of simple logic to map from one set to the other, from ASCII to our tiles. So that's basically what happens, and you can see here that the transaction length is 2 plus the length of the string times 2. That's because we send our address, which is 2 bytes, and then we send our string. But remember, for every character, we're sending 2 bytes, and then times 8 to give us a number of bits for the transaction. So the transaction is sent in bits, and we use some semaphores, basically some signals, to indicate that yes, we should send now, or no, we should not send. One important thing I had to learn here also was how to send data using interrupts. So this application on the ESP32, we're going to wait until we get a signal from the FPGA that it has entered its blanking period. So the FPGA will not be reading anything from memory, and that's when basically it's safe for us to write new data to memory. Again, works very similar to how the NES works and the Super Nintendo works, and I think a lot of other earlier gaming systems would send updated data to VRAM during the blanking period. So that's what we're doing here as well. So as soon as we get the signal that that we're in that blanking period, we have the interrupt set up here. That interrupt is a vBlank handler. It's tied to a specific GPIO pin, which is connected between the ESP32 and the FPGA. We've signed up a semaphore from the instruction set, interrupt servicing routine, that calls this task here. And tasks are sort of like threads within the ESP IDF. And so it gets the signal, it'll count the interrupts, and goes ahead and sends whatever data is ready to be sent in our SPI transaction. So that's, high level how the software works here. Like I said, I really would like to get this brought into Arduino. I think it's a lot more approachable. You can also run the ESP IDF through the command line, but at least I found on Windows the experience in Eclipse is a lot better. One big reason for that is, you see here I have a terminal. So within my terminal I can actually connect to the ESP32 that's on the chip, and I can continue to receive regular updates from it on serial. And compared to using the command line, here if I go ahead and I want to send a new build of the software to the ESP32, Eclipse knows that it should pause the console, the serial console, while it writes over the data, and then it'll rerun the serial console again. So I don't have to deal with the contention of making sure to remember to turn it off and turn it on every time I want to send new software over to the ESP32. So for development purposes, this is much, much easier. All right, so that is the software. Now let me tell you about everything that doesn't work. So, so this is our kind of how far I've managed to get with the data output. And maybe if you've been watching closely, you've noticed every so often there'll be a little glitch in the text here. So sometimes a random character will disappear and everything to the right of that character will shift to the left. There you go. So you saw that there it happened again. So I don't know yet why this is happening. It is very intermittent. I've had a very hard time debugging it. My concern, obviously in addition to not looking good and not being right for a demo, I want to be able to send arbitrary data over to the VRAM, including, scrolling information, sprite information, palette information. And if any of that data ever comes incorrectly, it's going to kind of mess up the whole system and nothing is going to look right. So we really need to be able to depend on it working. And so I have to figure out, and I have yet to figure out, but I do have to figure out what is going on here and what I need to do to get it to work right. Speaking of things not working right, as you can see right now, I have it set up so that my background layers are scrolling continuously in a single X direction, right? They're just constantly moving to the left. So I don't know why this is, but if I turn off the scrolling, so the scrolling which is implemented in hardware right now, if I turn off that scrolling, it stops receiving data over SPI. And that doesn't make any sense to me. Like I said, those systems for reading data on the graphics side and writing data over SPI are really completely separated from each other. I have no idea why this is happening, and it's going to require some further investigation. I think I have ideas for a few different permutations, variations of the design. I'm just trying to kind of figure out what causes it to work versus not work, and I think for me that's going to be a starting point for being able to dive deeper and try to find a solution to what's happening. So yeah, so a couple of things, important things not working right still. Nevertheless, this is a tremendous amount of progress, and I'm really happy with it. Seed Studio has not supported this kind of setup. If you read their documentation for the Spartan Edge Accelerator, they want you to plug in your own Arduino, and definitely that I think that's easier, but I really want a fully self-contained solution where you can just buy a board and it has everything you need. And the ESP32 is a powerful piece of hardware, and I think we have some proof here that we can get the kind of communication that we need between those two chips. One other thing that I can walk you through. So in addition to setting up some of my own test benches, which have been very helpful, honestly, for debugging some behavior without having to write to the device and then debug it using the logic analyzer, I did set up, I think some of the things I was just talking about with respect to the hardware buses and receiving data and sending the data might be easier to understand if instead of just talking about the code, we can just look at the signals. So I think I already have this set up in the waveform debugger. Let's quickly just check, and I think the ILA is configured for us to take a look. If it's connected, it's connected. Okay. So, there we go. Okay, we got our ILA up. I'm going to resize this window so we can see a little more of our signals. All right, I got my trigger set up on output RAM right. So this is a pulse that goes to the RAM chip to let us know, to let it know that we want to write some new data. So that comes on the rising edge there. And let's capture our 1024 samples. And this might help explain what's going on. So here you see, first you see the address here. So the address, like I said, we start at 21C0 like you saw in the ESP32 code. And every time output RAM write pulses is a signal that the data is there and the address is correct and the data is correct and it's ready to be written to RAM, right? That word, that 16-bit word is ready to be written. So you can see we go 1013, 1007, 1014, 1078, and so on all the way down. Just as a reminder as to what that means. Let's just zoom this in for a second. So you might remember that the the date that's being displayed here is currently Thursday, space DEC. So you can see that actually if you look at this. So remember, the way I set it up, the alphabet starts, the letter A is at address 0. So you can see hex 13, which is, in decimal is 19, which is the 20th letter of the alphabet, which is a T. Then you have the 8th letter of the alphabet, which is an H, and the 21st, which is a U. 7-8 is a space, and then D, the 4th letter. 5, the fifth letter is E, and then C, which is the 3rd letter. So you can see here, we can actually see the text that's coming through that represents that string that we're displaying on the screen. So that this might make it just a little easier to understand what's going on. And unfortunately, the way that the ILA works, it doesn't show us the names of the states, but it does enumerate them. So you can see here that as the data comes in and it comes through its different pulses and phases, you can see we move through the different states every time. So output RAM write goes up during state 4, comes back down in state 5, then we increment the address in state 6, so 21C0, the address becomes 21C1 at this point in state number 6, and then we wait for data, which is state number 2, once again. So that's really kind of in a nutshell what's going on with the hardware design. And was there anything else that is worth sharing? Well, yes, a couple of important things. So everything that I've shown you today has already been checked into the GitHub repository right here. And so all the FPGA code that does everything we talked about with this QSPI that writes into FPGA into the block RAM, it's all there. And the ESP32 application is its own repository. This is linked from the other one, and this one links back to the other one as well. So shouldn't run into too much trouble finding one from the other. But this does everything that is exactly this code that's here in Eclipse for me. So hopefully you all have a chance to check this out. I'd love to know if you're able to get the application to actually build and run in your own environment. I've gotten some feedback on that in the past, which I really appreciated, to help me figure out, what it would take to get this to be portable from one computer to another. And hopefully this is the beginning of some further explorations into how we can really take advantage of all the hardware that's on this board. There's a lot of work to do, right? There are the bugs that you can see that need to get fixed on the existing system, and then we can start to do some really really fun stuff. So I really think this is just the beginning of some pretty exciting stuff. So I realized I had the display get covered up here by the HDMI input, but you can see, so this is all on GitHub, right? It's under Spartan Edge Accelerator Graphical System, and it's under Spartan Edge Accelerator ESP32 QSPI to FPGA. So these are the projects. Please check them out. I've already been documenting issues, areas of improvement, and project management under issues and projects. Hopefully you get a chance to either leave a comment on YouTube or let me, reach out to me on GitHub. Really, however you can get in touch, I'm listening, and I'd love to have a conversation about some of this stuff, especially if you think you might be able to help me fix some of the bugs that I'm running into. I definitely think, as a kind of a rookie to the world of Verilog, I could easily just have a bug in my state machine and not even know about it. So thanks everybody. Hope you have a good night.